So hello everyone, in the previous session of binary search trees we have studied what is a binary search tree and how it is different from a general binary tree and what are the additional properties which makes this BST efficient data structure in terms of searching, in terms of performing operations in it when compared to general binary trees, right? So in this session what we are gonna do is we are going to solve some questions which are based on the concept of BST. Right, now let us start with our first question, and the name of the question is route to Leet's path. So what this question basically says is that this is my route, right? So I need to print all the paths is nothing but basically routes which lies I need to print all the routes which lies in the path of from a particular root node to a particular leaf node. Whatever the nodes lying in between this, I need to print those nodes. That is nothing but a particular route or you can say a path between this root to this corresponding leaf. So in this tree, if you observe, we have three leaves: leaf 1, leaf 2 and leaf 3, right? So this can be my path 1, this can be another path, and this can be another path. So here the total number of paths are 3, and whatever the nodes that lie between this path 1, path 2, path 3, I need to print these nodes. This is the basic asking of my question. So in path 1, what are the nodes? In path 1 is first of all my root node 8, after it 5, after it my leaf node 3. So this will become my path 1. After the path 2 will be first of all this root node, after it 5, after it leaf 2 6, and the path 3 will be root node, that is 8, after 10, after 11, after 14. So these are the three different paths, and the nodes which lies in between this path, I need to print those nodes. This is the basic asking of the question. I hope you have understood what is being asked in the question. Now let us talk about the approach, how I'm gonna do this particular question. So talking about the approach, what is the basic asking in my question? There is a particular root and there are n number of leaves, and from this root node to this leaf node, whatever the nodes lying in between this, I need to print those nodes. This is the asking of my question. Now to print those nodes, what I have to do, I need to perform some iterative approach or recursive approach, and I need to go through each and every node, and as I go through, I need to add that particular data structure, that particular node into some array or array list, whatever it might be. So what I'm gonna do is that first of all I will create a array list. I will create an array list of node type or integer type. I can create any type. So let's say I'm creating integer type array list. Let's say that the name of the array list is path. So in this path array list, what I'm gonna do is, as I iterate, as I move from root node to the next node, what I will do is that I will store its root node or nodes data. So initially I'm at root 8, right? So let's say this is my array list. This is my array list path. Now what I will do is that I will iterate through each and every node, and as I iterate, I will add that particular node's data into my array list. So first of all, initially I am at root 8, right? So what I will do is that the step 1 is add node to path. So this is my initially I am at node 8, so I will add its data. So I will add 8. After the second step will be go to the corresponding left part. So for root 8, its corresponding left part is 5. So I will come to root 5. As I come to root 5, I will add its data into my array list. So I will add 5 into my array list. After that, again, this is a secondary root, this is a root in itself. So if I reach a node, then what I will do is I will go to its left part. So this 5 will recursively call the left part, which is 3. So for this node 3, I will add node 3 data, which is 3 in my array list. So I will add 3 into my array list. Now you can see that for this node 3, there is left child is null, right child is null. So if it is null, what I will do is that I will return back, and I will print this, whatever the elements. If I reach a leaf node, then whatever the elements are there in my array list which I have added, I will print those as my output. So let's say this is my output screen. So first of all, as I reach my leaf node, you can see that I have at third node at root 3, I have reached my leaf node. So if I reach my leaf node, what I will do is that I will print the path array list. So what are the elements are there in my path array list? 8, 5, 3. So I will print that. After printing that, I will come back. I will come back to my previous function call. So I am at root 3. I am at root 3, right? I am at node 3. So its previous function call is 5. So I will return back to 5. So for this fifth node, the left part function calling is completed. If left part function calling is completed, then what I will do is I will go to the corresponding right part. If left part is completed, then go to its right part. So from 5, I will recursively call this sixth node. Right? As I call sixth node, I will remove 3. And I will add 6. Now you can see that 6 is a leaf node in itself. If it is a leaf node, whatever the elements present in my path array list, I will print those elements. So I will print 5, 8, 6. Now after that, I will recursively call back to my function, and as I call back, I will remove 6. So my array list will become 8, 5 now. Now here for this node 5, let me change the pen. It is becoming a kind of messy, right? So yeah, it might, if I draw the same thing with the same ink, it might become a little bit confusion. So at my node 5, my left part function calling is completed. My right part function calling is completed. So I will recursively come back to my previously called function. So previously called function is 8. So I will come back, and as I come back, I will remove 5. Now my array list is with only one element, okay? I have only one element in my array list, okay? Now you can see that for this 8th node, the left part is completed. The left part function calling is completed. If the left part function calling is completed, then I will go to its right part. So this 8 will call 10. And this 10, there is no left part. If there is no left part, then it can't call its left. So it will call its right part. So this 10 will call its right part. And similarly for this 11th node, there is no left part. If there is no left part, then it will call its right. So this will call right. And as I call, I will add those elements into my array list. So I will add initially 8, right? As I call 10, I will add 10. After it, I will add 11. After it, I will add 14. Now you can see that this is my array list. This is my changed array list, right? At the level of leaf 3. Now you can see that at 14th node, at this particular node, I have reached my leaf node. If it is a leaf node, what I will do? I will print whatever the elements present in my path array list. So these are the elements present in my path array list. So I will print those 5, 10, 11, 14. So I will print this. After printing, I will recursively come back. And as I come back, I will remove the element. So I will remove 14. After this 11 will call 10, come back to 10, and I will remove 11. Now this 10 will call 8. So as I come back to my previously called function, I will remove 10. Now this 8th function will call the main function. Now will return the value to the main function. After as it return the value to the main function, I will remove 8 also. So finally my path array list will become empty, and you can see that in the output screen I got the output. So this is what I'm gonna do. Now I hope you have understood. What I did is, this is my root node, right? Overall root node. Initially what I did is, I have created a array list, and initially the array list is empty. Now this is my root node. I have my root node as my function parameter. Whatever the function I am creating, a recursive function I am creating, I will pass its root node. And as I pass its root node, I will call its left function. I will call its left part. And this secondary root, you can see that the secondary root is 5. So this 5 will call 3. Now as I call this recursive function for the left part, whatever the elements I am calling, whatever the root elements I am having, I will add those in my array list. As I add my array list, I will keep on adding these elements into my array list until I hit my leaf node. If I got a leaf node, then whatever the elements present in my array list, I will print those. After that, I will come back to its right part. And again the same recursive function will continue for my right part also, and as I call the same recursive function for the right part, I will add those elements into my array list. And until I hit my leaf node, I will keep on calling my recursive function call, and if I hit my root node, if I hit my leaf node, hit my leaf node, I will print whatever the elements present in my array list. I will print those elements. I hope you got the approach. Now let us code this thing. Now first of all, I am gonna create a function, public static void print root to leaf. Print root to leaf. In this I will pass my root node and array list. So node root, after that array list of, let's say that I am passing integer type array list, integer, and let's say the name of the array list is path. Now what I will do is that I will check if my root is null. This will become my base case. If the root is null, if root is equals to null, then what I will do is I will basically come out of my function, because if root itself is null, then there will be no path. Okay. Now after that, what I will do is I will check, after I will add my root node into my path. So I will add root dot data. Now I will check if my leaf, if I hit my leaf, then I will, whatever the elements present in my array list, I need to print those elements. So I need to check for the leaf condition. So this is a leaf condition. That is, if root dot left is equals to null and root dot right is equals to null. If this both are null, then I need to print my array list, right? So I will call a function print. In this I will pass my print path function. In this I will pass my path, and this function will print my overall array list. Whatever the elements present in my array list, this function will print it. Now I need to call its left part. So I will call the same function print leaf for the root dot left, and print dot leaf for the right part, print dot right. And after that, I need to, at the last, I need to add the element, whatever the element it has returned, I need to add that. So I will write path dot remove. As I come back, as I recursively come back, as I coming back to my previous function call, I need to delete the last element. You can see that in the dry run I have deleted the last element in my array list. So here I need to remove path dot size -1. This is what I am doing. And let me print my function to print the elements present in my array list. So I am creating my function public static void print path. In this I will pass my array list of integer path. Now I will run a loop for int I is equals to 0 and I should be less than path dot size I plus plus. In this I will print system.out.print and print my path element, whatever the elements present in the ith position I will print that. So path dot get ith element and give a space in between, right? This is what I am doing here. I need to give void void. Now in the main program, what I am gonna do is I have my root node. Now after I am gonna call my function path to leaf, and here I will pass my root node and a new array list of integer. I am passing a new array list here. Now let me save this. It is showing some kind of error. Okay, here first of all let me create the array list first. On top let me create the array list of path is equals to new array list. Now after creating path, here I will pass my path array list, that's all. Now let me save and run. So if I run this, then you can see that I will get the output as I dry run before. Here in the place of space, let me give a arrow. It will look good. If I give arrow, it will look good. Now let me save and run this program. So it is showing some kind of error. Okay, here I need to give statement terminator where here. Okay, now let me save again and run. It is showing, okay, here I need to give root here I need to give root. Okay, now let me save it again and run. And after running the loop, here let me give again one line, because I don't want a mess in my output screen. I am getting my output, but I don't want in the same line. So you can see that this is my path. These are the different paths I am getting, right? 8531, 8534 for this particular tree, for this tree which I have created here, for this particular, where is my main node? Yeah. So for this BST, these are my number of paths, right? I hope you have understood overall working of the code. So this is how I will calculate by this, by writing these two functions. Basically one function, I am using one function to print the path, to print my array list. I am using another function. So basically by just writing this one function, I can print whatever from the root node to the corresponding leaf nodes, whatever the elements present, I can print those elements by just writing this simple function. I hope you have understood the logic. Now let us talk about another question. Now in this question, user will give us a BST, user will give us a binary search tree, and we need to tell that whether it is a valid BST or not. If it is a valid BST, then I will return true. If it is not a valid BST, then I will return false. So in this we need to check. The user will give us a tree, the user will give us a root node, and we need to iterate or whatever operations we are going to perform. We need to perform those operations, and after performing those operations, I need to tell my user that whether it is a valid, it is an actual BST, or it is just a binary tree. I need to tell my user. So I want you guys to think about this question. Pause the video right now, think about it for 2 minutes. Think what will be the approach, right? Like, so I have told you that in BST is a, you can say, an enhanced version of binary tree, because a BST is nothing but a binary tree, and along with a binary tree it follows some additional properties, and because of this additional properties we call a particular binary tree as a binary search tree. It means that, let's say that there is a binary tree, I have given you a binary tree. Now I want you to check whether it is a BST or not, whether it is a binary search tree or not. How you can check? You can check those particular binary tree whether it is a BST or not based on the properties. If it satisfies all the properties of BST, then it is a valid BST. If it doesn't satisfy any one of those properties, then immediately you can tell that this is not a valid BST. Right? This is what our approach is going to be. Right? We will check, we will make some in our code we will write some conditions, we will try to make some logic out of it, and by making logic, what at the very basic level we are doing is we are checking the conditions. Whatever the conditions we are having, whatever the properties we are having, we are checking those conditions, and after checking those conditions we are gonna tell that whether the particular binary tree is a valid BST or not. Now I want you to recall those properties. What are those properties? The first property is every BST is a binary tree. Every BST is a binary tree first. If the user has given you a tree which has 3 branches, it's not a binary tree in itself, so immediately return false, right? The second property is that the root node should be greater than its left node or left part, and the third property is that root node should be less than its right part, and the fourth property is that the left subtree and the right subtree, whatever the subtrees I am having, those particular subtrees should also follow the properties of BST, right? If it follows these 3 properties, if the left subtree, right subtree follows these 3, the top 3 properties, then finally our given binary tree will become a BST, valid BST. Else, if it doesn't follow, then it is not a valid BST. This is what our logic going to be. Now I need to check these 3 properties, particularly these 2 properties, root node left part, root node right part. If I got the answer as valid, if those properties of that particular tree satisfied, then I will return true. Now let us talk about our first approach. I hope you have understood what is a valid BST and what is the asking of the question. Now let us talk about our first approach. So in the first approach, if you think intuitively, if you think at the very basic level, you will get an idea that this is my root node and this is my left part and this is my right part. So for each and every root node, from its perspective, I need to check its left part and its right part. If the root node is greater than the left part and less than the right part, then it is a valid BST. So as I will iterate, and as I iterate, I will check for each and every node, for each and every root node, I will check its left part, right part. If both are satisfied, then I will return true. This is the basic logic we will get, right? But this logic, this approach has a problem. What is the problem? Let us take an example. Let us take that this is my BST. Okay, this is the given tree I am having. 1, 4, 5. Now I said that for a particular root node I need to check its left, right. So for this root node I will check its left 2, okay, right, and the left part, the right part is 5, greater. Okay, both are satisfied. Now I will check for this particular node. For this particular root node, the left part is less than the root node. Okay, good. The right part, the corresponding for this particular root node, the right part is greater. Right, good. So if for this particular tree, if I follow the first approach, then for this particular tree, my output will be true. Now if you observe very clearly, this is my tree, right? This is the example I have taken, 2, 1, 4 and 5. So this root 4 is lying on the left side of this root node. This node 4 is lying on the left part, and you can see that this is my root part. So the 4 value is greater than the root node. This left value is greater than the root node. It means that there is a node which is lying on the left side and it is greater than the root node. So this should return me false. But my approach 1 is giving me true. So the approach 1 is somewhat, it will like solve the questions, but for many questions you can see that for this basic example it is giving me the wrong answer. So this approach 1 is kind of failed. Now let us talk about the second approach. So before going to the second approach, there is a special property. I want you to remember that special property. Go to the session 1. If you don't remember the first special property, go to the session 1. So in the session 1, I have told you that a BST, if you run a in-order traversal for a given BST, if you run in-order traversal for this particular BST, then my output should be a sorted order elements. So if I run in order, then I will get the elements, I will get the data in the sorted order, right? So for a particular given tree, the user has given me tree, right? So I will call the in-order function, and after calling the in-order function, I will print those elements, and if those printed elements are not sorted in the ascending order, then that particular tree is not a BST. This is the basic logic. This is the basic like you can think of, and this is a shortcut also. This is the simple logic, and I want you to code this thing, right? Whatever the tree user will give us, perform in-order traversal in that particular tree, and if the output is sorted in ascending order, then it is a valid BST, else it is not a valid BST, right? This is the very basic code you can think of, and this will work 100%. Right? Otherwise it is not, even though it is not our approach 2. Approach 2 is kind of different. Now let us talk about approach 2. So let us consider, to understand what is this approach 2, let us take an example of a tree. Let's say this is my tree, 5, 3, 1, 4, 6 and 7. Let us say that this is my one of the trees. Now I need to check for this particular tree whether it is a valid BST or not. Now what this approach 2 says that the maximum value in the left subtree should be less than my root node. It means that let's say that this is my root node, right? So it has a left part and it has a right part. So in the left part, the maximum value, how many, let's say there are 10 nodes I am having on the left part. So among these 10 nodes, which one is maximum? I will take that. And after taking this maximum value on the left part, I will check that particular value with the root node value. If it is less, then yeah, the left part condition is satisfied. Now I will check for this root node its right part. In the right part, the minimum value the minimum value in the right subtree should be greater than the root node. So in the left part, in the right part, what is the minimum value I am having? I will take that particular node and I will check the root node. If my root node is less than the right part's minimum value, then both conditions are satisfied. Left part is satisfied, right part is satisfied. If both are satisfied, then I will return true as my output, else I will return false. Now you can see that for this particular root node, for this particular tree, I have taken the example. You can see that its left part maximum value is 4. This is my left part max value, and you can see that in the right part the minimum value, right part minimum value is 6. You can see right part minimum value, and my root node is 5. So you can see that my root node is greater than the left part maximum value. Okay, correct. And my root node should be less than my right part minimum value. Yeah, both are satisfying. If both are satisfying, then I will return true as my output, else I will return false. This is our approach too. Now what I will do is that for each and every, talking about the code, what I will do is that for each and every node I will create 2 variables, that is minimum variable and maximum variable, and according to the at what level I am in, I will check for each and every node what is its minimum value and what is its maximum value. You can see that for my root node it can be minus infinity, it can be maximum plus infinity, so it don't have any restriction. So if it doesn't have any restriction, then I will initialize it with null. So for this particular root node, the minimum can be anything, it means that it is null, and the maximum can be anything, so it means that it is null. Now I will come on the left part. So for this root 3, the minimum value, it can be anything. If it is on the left part and it is having minus infinity, yeah, the condition will satisfy. So it don't have any minimum restriction, it can be anything because it is lying on the left part. So the minimum can be anything, it means that null. And maximum, for this particular root 3, what is the maximum? It is lying on the left part, and my condition of BST is that root node should be greater than the left part. So the maximum value it can have should be less than 5. So the maximum will become 5 here. For this root 3, the maximum is 5 because it can't exceed 5. If it exceeds the value of 5, then it will not become a valid BST. I hope you got the logic. But it can be, it don't have any minimum restrictions. It can be as value as minus infinity, right? I hope you got the logic here. I hope you got the logic. Now I will come to its left part, the root node left part. So for this root node left part, its minimum value can be anything. It can be minus infinity also. If it is minus infinity, it can satisfy, right? So there is no minimum restriction, and the maximum restriction is that for this root node 1, its root value is 3. So it can't exit its root value in order to become a valid BST. So its maximum value will become 3. Now you can see that here for this root 4, the maximum value is 5 because it is lying on the left part. So if it exits the value of 5, then I will reach this condition. Here you can see that this particular node is exiting the root value. I don't want this condition. So its maximum value is 5 and the minimum value is, you can see that the minimum value should be greater than the root node. So here for this particular node, its root node is 3. So the minimum is 3. It means that for this node, 4th position, it can have the minimum value as 3 and the maximum value as 5. So whatever the values which lies in between this range, it can take any values. If it decreases, if I am assigning a value which is less than 3, then it will not become a valid BST. If I am assigning a value which is greater than 5, then it exits the main root node. And if it exits, again it will not become a valid BST. Right? Okay, coming back to our right part. So you can see that here my minimum value should be for this root node is 5. It means that it can have a value which is greater than 5, and the maximum is, it can have plus infinity as well. So it is null. It can have any value. Now for this right part, the minimum is 6, right? The minimum is 6 and the maximum can be anything, null, right? So what I'm doing is basically I'm creating for each and every node, I'm creating two variables, minimum and maximum, and I'm checking for this particular node what are the boundary conditions, what is the minimum and maximum conditions, and after like taking consideration of minimum and maximum, I'm checking its node value. This is it for a particular node, this is the minimum condition and this is the maximum condition. I have those conditions. Now I will check its root data, I will check its node data, and whether its data is satisfying this minimum and maximum properties. If it is satisfying, then I will return true, else I will return false. Now I hope you got the logic. Now let us code this thing. So here I will create a function, let me create a function, public static boolean type function, boolean, because I am returning true or false, right? So boolean is valid BST, is valid BST. In this I will pass my root node, root. After it I will pass my two variables. Let's say I am creating the same type node min, after it node max. These are the two variables. Now I will check if this will become my root base case, that is if my root node is itself null, it means that it is a valid in itself, so I will return true. If it is null, then if my root node itself null, it means that there is no tree, right? So I will return true. Now what I will do is I will check the conditions. If my minimum is not equals to null, if my minimum is not equals to null, it means that I am on the left part, and the root dot data should be less than or equals to minimum dot data. If it is not null and it is having some minimum property, it means that I am on the right side of my tree. If I am on the right side, then it should have a minimum value, right? Let's say my root node is 5 and I am on the right side. So if it is a valid BST, then whatever the values I am getting on the right side, it should be greater than my root node, it should be greater than 5. So if I am on the right side, if this right side value condition is satisfying, then I will return. If it is not satisfying, then I will return false. And the second condition will be if my maximum is not equals to null and root dot data is greater than or equals to my max dot data. If this condition is satisfying, then I will immediately return false. Now I will check, whatever the value returned for the left part and the right part, if both returns true, then and only I will return true. If any one of these parts return me false, then I will return false. So I will call the same function for the left part, and here the maximum value is root because it can't exit the root value, and is valid root dot right, and here the minimum value is root. I hope you got the logic here, right? Maximum value. And in the main function I am calling here, let me remove this, and I am calling is valid BST, and I will pass my root node after it both as min as null and max as null, and whatever the value that got returned, I will print that value. System.out.print, I will print that particular value, right? So this is the overall structure. Now let me save, and here I have given the okay another bracket. Now let me save and run. So you can see that if I run this code, then this is a valid BST. I am creating a valid BST by calling my insert function. So if I run this, then I should get my output as true. Now let me save and run. So you can see that I got the output as true. So this is how I will check. By just writing this function, I am checking that whether the given BST, whether the given tree is a valid BST binary search tree or not. I hope you got the logic. Now let us talk about another question. Now in this question, what user will do is that user will give us a binary search tree. user will give us a whole binary search tree and we need to print its mirror image. And what I mean by mirror image is that, let's say that you are standing in front of a mirror. So if you observe in mirror, you can see that you will get an inverted image. What I mean by inverted, not vertically but horizontally, you will get an inverted image. And what I mean by inverted is that, let's say that this is a mirror. This is a mirror. Now if you observe this mirror very clearly, you will observe that my left part is at the right position and my right part is in the left position. You can see that my left and right are kind of swapped, right? If you observe this in the mirror, this is what will happen, right? Left part will appear on the right side and right part will appear on the left side. So a inversion, you can say, happen, horizontal inversion will happen. Similarly, you can see that this is my BST, right? This is my root node and this is my left part and this is my right part. Now if you put in front of a mirror, then you will observe that the left part and the right part are kind of you can say inverted horizontally, or you can say swapped. You can see that the right part is coming on the left part in the mirror side, and the actual left part is coming on the right side. In the mirror, it is coming on the right side. So this right part is coming on the, this left part is coming on the right side in the mirror view. This is what our mirror will show us. Now again, this is not a valid BST, even though we need to print those elements. We need to give this data structure. We need to write a code to print the mirror of a particular BST. This is the basic asking of my question. Now I hope you have understood what is the mirror of a BST. Now let us talk about the approach of this question. So before talking about the approach of this question, let us understand this question in a deeper level. So to understand this question, let us take a basic example, very basic example. Let's say that this is the node you are having, this is the BST you are having, 8. Now if you put this BST in front of a mirror, then your output will be 8 and the left part comes on the right side, right? So this right part will come on the right side. So this 8 will come on left and this 2 will come on right. So this will become my output. I need to print this output. This is a mirror image. This is a mirror image of my BST and I need to print this. So for this basic tree structure, for this basic BST, my output will look like this. Whatever the left part I am having, that left part will come on the right side. And whatever the right part I am having, that right part will come on the left side in a mirror image, right? Now let us take some complex image. Now let us take some complex image as this 5 I am having, and it is having some left part. Let's say this is my left part. Left part I am having some elements, and the right part I am having some elements. So what I am gonna do is I will create a recursive function, and what this recursive function will do is that it will store the left part and it will store the right part. And after storing the left and right part, you can observe that in the mirror image, the left is coming on the right side and the right is coming on the left side. So I will swap these two values. This is what I'm gonna do. So this is my left part, right? This is my left part and this is my right part. So I will call my recursive function. I will create a function, let's say that mirror. So this mirror function will return a whole tree or a particular node, and whatever this mirror function will return, I will store in a particular variable. Let's say I am storing in a left side. I am creating a new variable left side. So this mirror will return this whole part to my left side. So I will call a mirror function and I will pass some parameter here, and this will return the left part. And after that I will store the right part as the same manner, in the same manner. So I will call the mirror function and I will pass some parameters. Now I need to keep faith on my recursive function that whatever the function I am creating, this will give the correct answer. I need to keep faith on that. Now after storing the left and right part, what I will do is that this is my root node, and if you observe that root node will not change, root node will remain the same. You can see that here this is my root node, and in the mirror image also I'm having the same root node on the same position. So what I will do is that I will change root dot left as my right side. I will change the whole left part with my right side, and after that root dot right is equals to my left part. I will store the left part on the right side. So what intuitively I am doing, what basically I am doing is that I am creating a function, let's say that mirror, and in that I will pass my root node, right? So I am creating a node variable, let's say node left side, and I will call the function mirror for the root dot left, and I will call the function node right side is equals to mirror for root dot right. So what this function will do is that it will return the whole left part of my given BST, and I am storing it in a variable ls, that is nothing but left part, and this function will return the whole right part of my BST, and I am storing that in a variable called as rs. Now what I will do is that I will swap root dot left is equals to rs. So whatever the value I am having in the rs, I will put it in the left part, and after root dot right is equals to ls. So whatever the values I am having, I will put that in the right side. This is what I am gonna do. And what will be the base case? The base case is that if I am reaching a null case, if my root is becoming null, if the root is null, then I will return from my program, come out of my program or my recursive function call. This is what I am doing, and this is the overall pseudo code. Now let us code this thing. Now I am gonna create a function public static void mirror BST. In this I will pass my root node root. Now what will be my base case? Here instead of void, let us say that I am returning the node, so I will give node. Now what will be the base case? If the base case, if root is null, if root is equals to null, then I will return null. That's all. I will come out of my function. Now I will call for the left part, so I will create node ls is equals to mirror BST for root dot left part. After node right side is equals to mirror, same function calling for the right part, root dot right. Now after what I will do is that I will swap. So I will write root dot left is equals to rs. After root dot right is equals to my ls. I am storing and I am swapping the left part with the right and the right part with the left. Now finally I will return my root node. That's all. Now in the main program, what I have created is I have created a tree and its mirror image, its mirror BST will look like this, something like this. Now I am calling my function, let me call the function mirror BST, and I am passing root. Now after passing, I am calling my pre-order function. So pre-order, and I will pass the root node, and whatever the root node it is returning, I am changing the root. So root is equals to mirror BST. I am storing, because this mirror BST will return a root node, right? So I am storing it in the root node. Now before calling the mirror, I am calling the same root node function. Now let me save and run. Let us see what output we will get. Here let me give the next line also, system.out.print. Okay. Now let me save and again run this. So you can see that this is my BST before pre-order sequence. This is my pre-order sequence of BST before mirror function calling, and after mirror function calling you can see that this is my tree and this is the output I got: 8, 10, 11, 5, 6, 3. So this is my BST, and this is how we will, by just writing this function, by just writing this mirror function, we can change, or we can make the mirror of a particular BST. This is how we will do it. Now let us talk about another interesting question. Now in this question, what user will give us is that user will give us sorted array. User will give us a sorted array, and we need to create a balanced BST out of it. Now this is the first time I think we are listening the term balanced BST. So what is the meaning of balanced BST is that balance is nothing but a BST which is having minimum height. That particular BST is considered as a balanced BST, and balanced BST is very important. When you are going to competitive coding, you have to create a balanced BST. And what I mean by balanced BST is that, let us consider this is my given array. Now I am iterating through each and every element, and I am creating a BST through our general method. Now let us say that this is my third element, right? So I am creating as the root node. You can see that the next element 6 is greater than my root element, so I will add it in the next side. And you can see here this is not sorted, so my element will be 5, 6, 8, 10, 11, 12. So this is the sorted. I think this is a slight mistake in the PPT. So I will add 5 on the right side. After 6 is also greater, so again 6 will come here, after 8 will come here, after 10 will come here, 11 and 12. So you can see that the height of this particular tree is high. And as I told you that BST is efficient data structure only if it is having, you can say, height as in a less. You can see, because whatever the operations we are performing in a BST, I have told you that its time complexity is big of h. Now you can see if I perform this operations in this BST, my time complexity will become big of n. And let's say that I am having elements as 10 to the power of 15. Now just imagine, for this number of elements my time complexity will become 10 to the power of 15. It means that I need to perform 10 to the power of 15 operations, and this is a skew structure. We call this structure, this BST, as a skew BST, and this is not efficient. If you create this kind of structure, this is not efficient. And what we will generally do is that we will try to make a balanced BST, and we can make a balanced BST by using some techniques, by creating some trees which is called as AVL trees, or you can say red black trees. We use this algorithms, we use these techniques to create a balanced tree in itself. This AVL and red black tree, what this will do is this will create an automate system of creating balanced BST. This is what they will do. Now we will study about AVL tree in the next chapter. Interesting topic. Come back for AVL trees, going to be like really interesting. But here what we are gonna do is that we will try to create a balanced BST. Now to create a balanced BST, let us observe one thing. So the thing, let me remove all this. I hope you have understood that if we create a BST using our general approach, my BST will not remain efficient as it used to be, right? It will give us big of n time, and if n is equals to 10 to the power of 15, then I need to perform 10 to the power of 15 operations in my BST, so it is not efficient. And one more thing is that balanced BST is a efficient data structure. Whenever you are creating a BST, you need to keep this in your mind that you have to create a balanced BST every time. Okay, now you can see that here, if you run operations in this particular balanced tree, it means that the height is minimum. You can see that the height of this tree is 3, and the height of this is, here how many elements I am having, 1, 2, 3, 4, 5, 6, 7, 8. So the height of this is 8. Now the thing is that in a balanced BST, the time complexity will become log n. Now if n is equals to 10 to the power of 15, then my time complexity will become log 10 to the power of 15, which is 15 to the power of log 10. You can see that 15 to the power of log 10 is much lesser then 10 to the power of 15. So whenever we are performing operations, we make sure that we should create a balanced BST, because a balanced BST will give us a minimum height, and whatever the operations we are performing in a BST, it is totally dependent on my height of the tree. If the height is minimum, then my operations will become efficient. If they are not minimum, if it is not balanced BST, then my operations will like take n number of time, large time, and it will not become efficient. I hope you have understood the logic here. Now let me remove the ink here and let us talk about how I'm gonna create a valid BST or balanced BST. So to create a balanced BST, let us talk about in order sequencing. I have told you that in order sequencing, this property is very important, and we are gonna use this property in many questions. In valid BST questions, we have used the property of in order. In this, we are gonna use the property of in order. So keep this, that whenever we are performing the operations of in order, this will give me a in order sequencing, right? So let us say that I am creating a tree. Let's say that I am creating a tree 5, 3, 1, 2, and 4, 8. Let's say 8. Now if I perform in order sequencing for this particular BST, then my output will be 1, 2, 3, 5, 8. Now you can observe that my root node is coming in between of this whole tree, in this whole tree. So what I will do is that the user has given me array, and I have extracted that in order sequencing, the middle element which comes in the in order sequencing will become my root node. So what I will do is that I will create a function talking about the approach. This is my array, right? So I will take the middle element 3, this is my array, 3, 5, 6, 8, 10, 11, 12. This is the given array. 0, 1, 2, 3, 4, 5, 6. So what I will do is that I will calculate, first of all, the first step is that calculate the middle element. Calculate the middle, that is starting index plus ending index divided by 2. I will calculate the middle index. So here the middle index is 3, right? So I will take that middle index, and whatever the element present in that middle index, I will make it as a root node. You can see that 8 is my root node and 8 is my middle index. So I will make root node is equals to middle index. Now 8 is my middle index, and it has some left part and it has some right part. You can see that I have some left part and I have some right part. So whatever the elements present on the left part, that element will those elements will become the part of my left subtree, and whatever the elements present on the right part of my middle element, those elements will become the right part of my tree BST. So what I will do is that, right, this is my tree, right, 5, 6, 3, 5, 6, after 10, 11, 8. So my root node is 8 now. This is my root node. Now I will recursively call my recursion function for the left part. So I will call for the left part. So for this recursive call, 3, 5, 6, this is my starting element and this is my ending element, and this will become my mid. So if it is mid, then this mid value will become my root node. So for this 8th node, the subroot is 5. I will make 5 as a subroot. Now you can see that for this mid value, it is having only one element. If it is having only one element on the left side, then it will become its left child. So for this root node, 3 will become the left child. After that, 8 will become the right, 6 will become the right child. Similarly, I will recursively call for this left part also. So I will recursively call 10, 11, 8, and you can see that this is my starting element, ending element, and this will become my mid element. Now here I will add this mid element as my right child, and after that, this starting, it is only one element, so I will write it on the left child, and here I will add it on the, this is actually 12, not 8. Okay, now I will add this. Let me remove this also. Okay, so I will add 10 on the left child, and after that I will add 12 on the right side. So this is how I will form my BST, right? I hope I have understood. So what I'm doing is that, let me remove all this thing, let me write the pseudocode. So what I'm gonna do is that I will create a function, public static whatever, create balanced BST. I will create a function here, BST. In this I will pass my root node or whatever the array, because I'm not having any root node, right? So I'm passing my given array, its starting index and its ending index. Now what will be my base case? My base case will be, if my starting index, I am recursively calling my starting index and ending index, and as I recursively call, I am changing the value of starting index and the ending index. So if my starting index become greater than the ending index, then I will immediately return from my program. This is my base case. Now what I will do is that I will calculate the mid value. Int mid is equals to starting plus ending divided by 2. After that I will call node root. I am creating root, right? So I will create a new node root, and it will become my array element, mid value element, right? Or I am assigning the mid value element as my root node. After that I will call for the left part. So root dot left is equals to create, the same function, create function. In this I will pass the same array, same starting index, but the middle element will get changed. I am passing the ending index as middle minus 1. After root dot right is equals to the same create function and the same array, but the starting index will get changed by middle plus 1 after the ending index. This is what I am doing in my function. I hope you have understood the overall approach. Now let us code this thing. So I am going to create a function, public static. I am going to return my root node. So static node create BST. In this I am passing my integer array, int ARR, int starting index, int ending index. Now after that what I will do is I will check my base case, that is if my starting is greater than ending, then I am gonna return null. I am gonna come out of my function. After that I am gonna calculate int mid is equals to starting plus ending divided by 2. Now after that what I am gonna do is that I will make the root node, int root, node root is equals to new node of ARR of middle element. Now my left function calling, so root dot left is equals to my same create function call, same array, starting element is also same, but the middle element will get changed, middle minus 1. For the left part I am calling middle minus 1. After root dot right is equals to create BST for the right part, that is middle plus 1 and ending element. Now after that finally I will return node, because my return type is node, right? So I will return a root element, whatever the root I am having, I will return that. This is my function. Now here I am gonna call my function. Here in the main program, let me remove all this. Now I am going to create an array int ARR, and I am going to take the example which we have taken. Now in the main program what I am going to do is I have created the array, and I have created the same array which we have taken the example, and we have dry run that. Now after that I am creating node root, and whatever this create function is returning, I am storing that. After that I am calling my pre-order function to print the elements in my given create tree. Now let me save and run. Let me draw the tree also, which tree I am creating here. So this is the tree I have created. Now if I run this pre-order sequence, then I will get the output as follows. Now let me save and run. So you can see that I got the output as 8536 pre-order sequence as this. Now if I run this in order sequence, then I will get the same sorted array. Now let me save and run. Here let me print a next line, system.out.print next line. Now let me save again and run. So you can see that I got the output as this pre-order, this is the pre-order sequence, and this is my in-order sequence. So this is how I will create a balanced BST by by considering the middle element, left part, right part, and calling my recursive function calling like this, which I have done. Now up to now we have solved some questions, we have understood what is BST, the concepts related to BST, and all those kind of things, and I hope you have understood, you have learned something, find it very interesting. I have tried my best to explain to you guys. Now in the next session, what we are gonna do is we are gonna talk about a new topic, you can say, and this topic is going to be really important, and this topic is going to be a really interesting topic at the same time, and the name of the topic is AVL trees. So with that being said, I will see you in the next one.